Hello and welcome to the session on Elements of Classical Mechanics, Part 2. Calculus of variation. Calculus of variation is used to find the curve for which a given line integral has a stationary or extremum value. Before discussing calculus of variation, first let us obtain an equation for the shortest path between 2 points on the curved surface. Let the 2 points be represented by x0, y0 and x1, y1. Suppose we have a function y is equal to I of x which represent any curve joining the 2 points, such that the function y of x satisfies the boundary conditions y of x0 is equal to y0 and y of x1 is equal to y1. Let it be equation number 1. Let us now consider two very close points on the curve separated by distance dl, where y dash is equal to dy divided by dx. The total length of the curve I is equal to integral from x0 to x1 1 plus y dash square the whole raised to 1 by 2 dx. We can evaluate this integral provided we know the value of the function y of x such that it satisfies the equation 1, which will make this integral minimum. We cannot apply the usual method of finding the minimum value because here we have to vary a function y of x and not a single variable. Derivation of Euler-Lagrange equation. Calculus of variation helps us to find a function y of x such that definite integral of a function of this function has a maximum or minimum value. Let f be a function of y and y dash which are themselves functions of x such that the dependence of y on x is not known. Consider an integral j is equal to integral from x1 to x2 f of y dash x dx. Let it be equation number 2, where y dash is equal to dy divided by dx. Thus, f is a function of dependent variable y, independent variable x and y dash is equal to dy divided by dx. Here j is called a functional of y of x. The value of j will be different along different paths connecting the points a and b. But our aim is to find the path of integration such that the integral has a stationary value, that is, we have to find a particular curve y of x for which the line integral has a stationary value relative to the paths differing infinitesimally from the correct function y of x. A curve y of x which satisfies this relation is called an extremal of j. The integral given in equation 2 is called the functional. The calculus of variations deals with the problems of maxima or minima of functions. The function j is extremum along the curve AB which represents y is equal to y of x. To see whether this value is an extreme value or not, consider a family of curves given by y of x alpha is equal to y of x plus alpha into eta of x, where alpha is a parameter and eta of x is an arbitrary differentiable function. This function should satisfy the conditions alpha of x1 is equal to alpha of x2 is equal to 0 at the endpoints. When alpha is equal to 0, the neighboring family of comparison functions. The vertical distance between the actual and the neighboring curve at any point is called variation of function y of x, keeping the value of x fixed. The required function for the neighboring curve is a function of alpha. J of alpha is equal to integral from x1 to x2 f of y of x plus alpha into eta of x, comma y dash of x plus alpha into eta dash of x, comma x dx. J of alpha is equal to integral from x1 to x2 f of y of x comma alpha, comma y dash of x comma alpha, comma x dx. Let it be equation number 3. The condition for obtaining a stationary point or an extremum for alpha is equal to 0 is that dj divided by d alpha at alpha is equal to 0 is equal to 0. Differentiating equation 3, dj divided by d alpha is equal to integral from x1 to x2 dou f by dou y into dou y by dou alpha plus dou f by dou y dash into dou y dash divided by dou alpha plus dou f by dou x into dou x divided by dou alpha dx. Let it be equation number 4. But dou x divided by dou alpha is equal to 0 because alpha is independent of x. Also y dash is equal to dy divided by dx. The second term in equation 4 is integral from x1 to x2 dou f divided by dou y dash into dou y dash divided by dou x dx is equal to integral from x1 to x2 dou f divided by dou y dash into dou square y divided by dou x dou alpha dx. Let it be equation number 5. Integrating by parts, integral from x1 to x2 dou f divided by dou y dash into dou square f divided by dou x dou alpha dx is equal to dou f divided by dou y dash into dou y divided by dou alpha between the limits x1 and x2 minus integral from x1 to x2 d by dx of dou f divided by dou y dash into dou y divided by dou alpha dx. All the neighboring curve above as well as below y of x must pass through a and b. Hence, partial derivative of y with respect to alpha at x1 and x2 must be 0. So, the first term on right hand side of equation 5 is 0. Substituting in equation 4, dj divided by d alpha is equal to integral from x1 to x2 dou f divided by dou y minus d by dx of dou f divided by dou y dash dou y by dou alpha dx. The condition for a stationary value is dj divided by d alpha is equal to 0, which is equal to integral from x1 to x2 dou f divided by dou y minus d by dx of dou f divided by dou y dash into dou y divided by dou alpha at 0 dx. But dou y divided by dou alpha is equal to eta of x and is an arbitrary function. Hence, the integrand must be 0. Dou f divided by dou y is equal to d by dx of dou f divided by dou y dash is equal to 0. This equation is called the Euler-Lagrange equation and its solution y of x is called an extremal. This is the condition which the function y of x must satisfy so that j has a stationary value. The quantity dou y divided by dou alpha at 0 d alpha is equal to delta y represents the infinitesimal departure of the varied path from the correct path y of x at the point x, and this corresponds to virtual displacement. The symbol alpha is called the variation and is used to represent variation increase in the quantity to which it is applied as we morph from the stationary path to the comparison path, keeping the value of x constant. Hamilton's principle. Hamilton's principle states that the path actually traversed by a conservative holonomic dynamical system from time t1 to t2 is 1 hour, which the integral of the Lagrangian between limits t1 and t2 is stationary. That is, the time integral of the Lagrangian is extremum. That is, integral from t1 to t2 L dt is equal to I, which is equal to extremum, where I is the extremum value of the time integral of the Lagrangian and is called Hamilton's principal function. The variation in I is delta I is equal to delta of integral from t1 to t2 L dt is equal to 0. This principle is used to identify the actual paths from the neighboring paths. Derivation of Lagrange's equation from Hamilton's principle. Let f be a function of independent variables yi dash, which are both functions of x with yi dash is equal to dyi divided by dx. The variation of the integral j is delta j is equal to delta integral from 1 to 2 f of y1 x comma y2 x comma etc comma y1 dash x comma y2 dash x comma etc comma x dx. Let it be equation number 1. We can find the value of the variation delta j by assuming j as a function of a parameter alpha. y1 of x comma alpha is equal to y1 of x comma 0 plus alpha into eta 1 of x. y2 of x comma alpha is equal to y2 of x comma 0 plus alpha into eta 2 of x, etc. Here eta 1, eta 2 etc. are independent functions of x whose values are 0 at the endpoints. y1 of x comma 0, y2 of x comma 0 comma etc. are the solutions to be obtained. The variation of j is given by delta j is equal to integral from 1 to 2 summation I dou f divided by dou yi into dou yi divided by dou alpha into d alpha plus dou f divided by dou yi dash into dou yi dash divided by dou alpha dx. Let it be equation number 2. Integrating by parts, the second term on right hand side we get integral from 1 to 2 dou f divided by dou yi dash into dou square yi divided by dou alpha into dou x dx is equal to dou f divided by dou yi dash into dou yi divided by dou alpha between the limits 1 and 2 minus integral from 1 to 2 dou yi divided by dou alpha into d by dx of dou f divided by dou yi dash dx. The value of first term on right hand side is 0. Hence, delta j is equal to integral from 1 to 2 summation I dou f divided by dou yi minus d by dx of dou f divided by dou yi dash into delta yi dx. Let it be equation number 3. But the variation of delta yi is equal to dou yi divided by dou alpha into d alpha are independent and hence cannot be 0. So, the integrand is 0. So, the condition for delta j to be 0 is that dou f divided by dou yi minus d by dx of dou f divided by dou yi dash is equal to 0, where I is equal to 1, 2, 3 etc. n. Let it be equation number 4. This is the generalized Euler-Lagrange differential equations for several dependent variables. Hamilton's principle can be written as I is equal to integral from 1 to 2 L of qi comma qi dot comma t dt. Because Lagrangian is a function of the generalized coordinates qi comma qi dot and time t. Let us identify the Lagrangian L to the function f of yi comma yi dash comma x with transformation yi transforms qi, yi dash transforms qi dot and x transforms t. Then f of yi comma yi dash comma x transforms L of qi comma qi dot comma t. While deriving equation 4, it was assumed that yi variables are independent. The corresponding condition in Hamilton's principle is that the generalized coordinates qi be independent. In that case, the constraints must be holonomic. The Euler-Lagrange equation corresponding to the integral I is obtained by changing f to L and y's to q's and x to t. D by dt of dou L divided by dou qi dot minus dou L divided by dou qi is equal to 0, where I is equal to 1, 2, 3 etc. up to n. This is the Lagrange equations of motion which we have derived from the Hamilton's principle. Problem. Find the differential equation of one-dimensional harmonic oscillator by applying the variational principle. Answer. For one-dimensional harmonic oscillator, the Lagrangian L is equal to t minus v, which is equal to 1 by 2 m x square minus 1 by 2 k x square. That is, L is equal to f of x comma x dot comma t is equal to 1 by 2 into m x dot square minus 1 by 2 into k x square. Integral L dt or integral f of x comma x dot comma t dt is extremum. Euler-Lagrange's equation is d by df of dou f divided by dou x dot minus dou f divided by dou x is equal to 0. Let it be equation number 1. Dou f divided by dou x is equal to minus kx. Dou f divided by dou x dot is equal to m x dot. D by dt of m x dot plus kx, m x double dot plus kx is equal to 0. M into d square x by dt square plus kx is equal to 0. D square x divided by dt square plus k by m into x is equal to 0, or d square x divided by dt square plus w square x is equal to 0. This is the differential equation for one-dimensional harmonic oscillator. Cyclic coordinates. The kinetic energy of the particle moving along x-axis is T is equal to 1 by 2 into m x dot square. Let it be equation number 1. Dot T divided by dot x dot is equal to m into x dot is equal to p. P is the linear momentum. If v is not a function of the velocity x dot, that is v is equal to v of x, and dou v divided by dou x dot is equal to 0, then the momentum p can be written as p is equal to dou by dou x dot of t minus v. P is equal to dou L divided by dou x dot. Let it be equation number 2. The generalized momentum corresponding to the generalized coordinate qk can be written as pk is equal to dou L divided by dou x dot. Let it be equation number 3. This is called conjugate momentum or canonical momentum. For a conservative system, the Lagrange's equations are given by d by dt of dou L divided by dou qk dot minus dou L divided by dou qk is equal to 0. Let it be equation number 4. Substituting for dou L divided by dou qk dot is equal to pk, we get dpk divided by dt minus dou L divided by dou qk is equal to 0, or pk dot is equal to dou L divided by dou qk. Let it be equation number 5. In the expression for Lagrangian L of a system, suppose a Cartesian coordinate qk does not appear explicitly, then dou L divided by dou qk is equal to 0. Let it be equation number 6. Hence, pk dot is equal to d by dt of dou L divided by dou qk dot is equal to 0. Let it be equation number 7. Integrating pk is equal to dou L divided by dou qk dot, a constant. Let it be equation number 8. Whenever the Lagrangian function does not contain a coordinate qk explicitly, the generalized momentum pk is a constant of motion. The coordinate qk is called cyclic or ignorable coordinate. Hamiltonian function. The Hamiltonian function h is given by h is equal to summation k pk qk dot minus L. Let it be equation number 1. In general, the Hamiltonian function h is the function of generalized momentum pk, generalized coordinates qk and time t. That is, h is equal to h of pk qk t. Let it be equation number 2. If t does not appear in the Lagrangian L explicitly, then dl divided by dt is equal to 0. Hence, dh divided by dt is equal to 0, or h is equal to summation k pk into qk dot minus L, which is equal to constant. Let it be equation number 3. If the time t does not appear in the Lagrangian L explicitly, then the Hamiltonian h is constant in time. This is a conservation theorem for the Hamiltonian of the system. Under special condition, the Hamiltonian h is equal to the total energy E of the system. Hamilton's equations. The Hamiltonian is a function of generalized coordinates qk, generalized momentum pk and time t. H is equal to h of q1, q2, etc., qk, etc., qn, p1, p2, etc., pk, etc., pn, t. Let it be equation number 4. dh is equal to summation k dou h divided by dou qk into dqk plus summation k dou h divided by dou pk into dpk plus dou h divided by dou t into dt. Let it be equation number 5. H is equal to summation k pk into qk dot minus L. Let it be equation number 6. dh is equal to summation k qk dot into dpk plus summation k pk into dqk dot minus dl. Let it be equation number 7. But L is equal to L of q1, q2, etc., qk, etc., qn, q1 dot, q2 dot, etc., qk dot, etc., qn dot, t. dl is equal to summation k dou L divided by dou qk into dqk plus summation k dou L divided by dou qk dot into dqk dot plus dou L divided by dou t into dt. Let it be equation number 8. But Pk dot is equal to dou L divided by dou Qk and Pk is equal to dou L divided by dou Qk dot. Substituting in equation 8, dl is equal to summation k Pk dot into dQk plus summation k Pk into dQk dot plus dou L divided by dou T into dt. Let it be equation number 9. Substituting for dl in equation 7, dH is equal to summation k Qk dot into dPk minus summation k Pk dot into dQk dot minus dou L divided by dou T into dt. Let it be equation number 10. Comparing the coefficients of dPk, dQk and dt in equations 5 and 10, we get Qk dot is equal to dou H divided by dou Pk. Let it be equation number 11. Minus Pk dot is equal to dou H divided by dou Qk. Let it be equation number 12. And minus dou L divided by dou T is equal to dou H divided by dou T. Let it be equation number 13. Equations 11 and 12 are known as Hamilton's equations or Hamilton's canonical equations of motion. For k is equal to 1, 2, 3 etc. up to n, in all there are 2n first order differential equations. If any coordinate Qk is cyclic, then dou H divided by dou Qk is equal to 0 or Pk dot is equal to 0 or Pk is equal to constant in time. Let it be equation number 14. Thus, for any cyclic coordinate, corresponding conjugate momentum is a constant of motion. From equation 5, we get dou H divided by dou T is equal to summation k dou H divided by dou Qk into Qk dot plus summation k dou H divided by dou Pk into Pk dot plus dou H divided by dou T. Let it be equation number 15. Substituting for Qk dot and Pk dot from equations 11 and 12 in equation 15, we get dH divided by dt is equal to dou H divided by dou T is equal to minus dou L divided by dou T. Let it be equation number 16. If the Lagrangian L and the Hamiltonian H does not depend on time t explicitly, then dou L divided by dou T is equal to minus dou H divided by dou T is equal to 0, and hence dH divided by dt is equal to 0 or H is equal to constant. Let it be equation number 16. For a conservative system, H is equal to T plus V is equal to E is a constant. Hamilton's equations in Cartesian coordinate system. Kinetic energy of the particle T is equal to 1 by 2 m x dot square plus y dot square plus z dot square. Potential energy of the particle V is equal to V of x y z. Lagrangian L is equal to T minus V, which is equal to 1 by 2 into m x dot square plus y dot square plus z dot square minus V of x y z. Generalized momentum Pk is equal to dou L divided by dou Qk dot. Px is equal to dou L divided by dou x dot, or x dot is equal to Px divided by m. Similarly, y dot is equal to Py divided by m and z dot is equal to Pz divided by m. Hamiltonian H is equal to summation k Pk Qk dot minus L. For k is equal to x y z, H is equal to Pk x dot plus Py y dot plus Pz z dot minus 1 by 2 into m of x dot square plus y dot square plus z dot square plus V of x y z, which is equal to Px square by m plus Py square by m plus Pz square by m minus 1 by 2 m into Px square plus Py square plus Pz square plus V of x y z. Hamilton's equations are Qk dot is equal to dou H divided by dou Pk and Pk dot is equal to dou H divided by dou Qk. The Hamilton's equations in Cartesian coordinates are x dot is equal to dou H divided by dou Pk, or x dot is equal to Px divided by m, or Px dot is equal to minus dou H divided by dou x, or Px dot is equal to minus dou V by dou x. Similarly, y dot is equal to Py divided by m and Py dot is equal to minus dou v divided by dou y, and z dot is equal to Pz divided by m, and Pz dot is equal to minus dou v divided by dou z. The equations of motion can be written as m x double dot is equal to minus dou v by dou x, m y double dot is equal to minus dou v by dou y, m z double dot is equal to minus dou v by dou z. Problem. Using Hamilton's equation, obtain the differential equation of a harmonic oscillator. Answer. For a harmonic oscillator, the kinetic energy T and the potential energy V are given by T is equal to 1 by 2 m x dot square and V is equal to 1 by 2 k x square. Now, L is equal to T minus V, which is equal to 1 by 2 m x dot square minus 1 by 2 k x square. Let x dot be replaced by the generalized momentum Px. Px is equal to dou L divided by dou x dot is equal to m x dot, or x dot is equal to Px divided by m. T is equal to 1 by 2 m x dot square is equal to Px square divided by 2m. Hamiltonian H is equal to T plus V, which is equal to Px square divided by 2m plus 1 by 2 k x square. X dot is equal to dou H divided by dou Px is equal to Px divided by m, or Px is equal to m x dot, and minus Px dot is equal to dou H divided by dou x is equal to kx, or Px dot is equal to minus kx. Substituting for Px, we get m x double dot is equal to minus kx, or m x double dot plus kx is equal to 0. This is the differential equation of a harmonic oscillator. Let me summarize the main ideas in this session. Calculus of variation is used to find the curve for which given line integral has a stationary or extremum value. Hamilton's principle states that the path actually traversed by a conservative holonomic dynamical system from time t1 to t2 is 1 over which the integral of the Lagrangian between limits t1 and t2 is stationary. The Hamiltonian function h is the function of generalized momentum pk, generalized coordinates qk and time t, that is h is equal to h of pk, qk, t. You can try these questions given here. First one, what is called conjugate or canonical momentum? Second one, state Hamilton's principle. Third one, what is Hamilton's principle used for? Fourth one, what are cyclic coordinates? Now you can go through these books for reference. First one, Engineering Mechanics 5th edition by J.L. Merriam and L.G. Craig. Second one, Mechanics, Statistical Mechanics and Relativity by Professor Vivekanandan P. Kadavu. Third one, Classical Dynamics of Particles and Systems 4th edition by S.T. Thornton and J.B. Merriam. Hope that you have enjoyed this session. We can meet again with another topic. Till then, take care.